so we're really moving now into the Fourier side, Fourier part of the course. Like I said, we're about 2/3 through. We've certainly seen Fourier a little bit, but now quite a lot in these lectures today and in wavelets. There'll be a series of lectures about signal processing and wavelets where Fourier methods are going to be crucial. Well, this is a topic called spectral methods. And it's not an area I worked in, so I was a little apprehensive about this lecture. But I found a delightful book by my friend Nick Trefethen called Spectral Methods in Matlab. The in Matlab part refers to the fact that in each section, whatever he does, he gives a Matlab, a neat Matlab code to do it. It's published by Siam and quite inexpensive, and really he's a terrific author. He was at MIT and he's now at Oxford. So I'm relying on this book. And maybe I start with the main question. Well, so what's the idea? Spectral methods are one more way to deal with differential equations, to make them discrete, to make them solvable. So the first, most basic question is, how do you discretize the derivative? Okay, so let's just remember how we've done it so far. Because we've been doing it right, but there are other ways to do it, and the idea of spectral methods is going to be high accuracy. It was just realized. So this spectral methods goes back to, I better put his name up here, Steve Orsog, and others, and many others since. Lots. Developed this idea that you didn't have to use just a 3-point scheme. You could use all the points and zip the accuracy way up. And so we need formulas. How do we, if we use 3 points, suppose we think about replacing the derivative du dx. Let's suppose we're on I practically have drawn here let's say an equally spaced mesh. Let's start with that. Spacing h. Typical point j. Typical neighbors j plus 1 and j minus 1. Typical replacement of du dx is what would be a reasonably good replacement, the kind that we've done. Maybe centered. U j plus 1 minus u j minus 1 over 2h. So if we have a differential equation and we see a first derivative in it, and we've got equally spaced mesh, that's a natural replacement, and it's a pretty decent. It's probably the best one we can create out of 3 points. And what about second derivative? Because our equations often have a second derivative in them. Well, then uj plus 1 minus 2 uj plus uj minus 1 over h squared is our old friend, good friend. And it's certainly the natural choice, the right choice for 3 points. Okay. Now, so my idea is to up the accuracy. So I need some principle to go on. Where did these come from, and where could better methods, higher approximations? And of course, we can figure that to increase so my first step up, once I get the principle established, will be to use not just the 3 points, but maybe 5 points. And it's natural to figure that if I choose the right formulas, I can represent the u dx and the second derivative and other derivatives too with more accuracy. If maybe these have sort of an accuracy of second order, and very likely with going up to 5 points, I can up the accuracy to fourth order. That will. I'm still in the world of polynomial accuracy. That is, with this finite fixed set of points, I'm not going to get spectral accuracy, infinite. Well, infinite is not quite what I mean. Infinite order accuracy. But first of all, the principle. What's the principle? How do I? So this is the governing principle of producing these formulas. Is what's my problem? I'm given the values at mesh points, right? Whatever. I'm given values of uj at the mesh points. So, but what calculus tells me how to take derivatives of is functions. What I need is a function. So the principle is create or interpolate, maybe I should say just interpolate the mesh values by a function or some kind of pieces of functions or whatever by function. And then what? Let me call it P of x. And then what? Then my du dx, my approximation to du dx. How am I going to come up with a derivative? Well, take the derivative of p, right? I've now got something I can. So is approximately p prime. And the second derivative of u, which doesn't really make sense because u is only defined on meshes. So but the good thing is that p is defined as a function, and if it's a simple function, as I would naturally choose, I can take its second derivative too, and I've got something. Okay, now, so I guess I hope that these formulas, which we sort of just wrote up there, and we checked by Taylor series that this is, if I expand this in a Taylor series around uj and this one and do the subtraction, then sure enough, the first term that'll pop out will be the u dx, and then there'll be terms that I miss by, and the first term I miss by will tell me the order of accuracy. Okay, so what function should I take to fit those? What function, what p of x should I take if I've got 3 points and I want to fit them by a function? Natural choice is a parabola, second degree function. If I'm going to use these three values, j minus 1, j, and j plus 1, and I fit those values by a parabola, well, I'm sorry, I've made this look kind of goofy here. Let me make it a little uneven. So now I've fit it by some kind of parabola, and the derivative of the parabola, the slope of the parabola, gives me my formula. Because, of course, the parabola just depended on those three values, uj minus 1, uj, and uj plus 1. So, I don't know if you want me to go through the step of figuring out the parabola, taking its derivative. Well, that we could sure do, right? And then recognizing that this is what comes out. Well, let me ask you, suppose I only, so it would come out. It would come out. And let me go up. Sorry? I'll go up 1 to 5 points. So just let's think, how would we get a 5-point formula for the first derivative, let's say? Right, polynomial x to the fourth. Exactly. I mean, it's neat to get this principle, because this is what I owe to Trefethen. Because once we got that principle, we really got the idea here. Okay, so we put a fourth degree polynomial. So example 1 would be P is a parabola matching 3 values at a time and giving the point in the middle. Well, of course, actually, yeah, well, all right, anyway, it's natural to take to sort of symmetrically. You figure, okay, it's smarter to use the 3 values, one on one side, the centered one, and the one on the right. Okay, so let's move it up to P equal fourth degree, exactly. Use 5 values. We're going to get some formula, as I said, that got to be classical. Newton would have known it for sure. So I think I remember what those weights turn out to be. Here the weights were 1 over 2h and 0 and minus 1 over 2h. I think the 5 values that when we fit with a fourth degree polynomial, then we take the derivative as our little principle says. I think the value that we would get, I think it's minus a 12th uj minus 2, or maybe plus a 12th, minus 2/3, I think. This is like a nice exercise, uj minus 1, and because it's centered, so centered and anti-symmetric, the first derivative, of course, we recognize as should like come out anti-symmetric, then we'll use 2/3 with a plus sign, uj plus 1, and minus a 12th, uj plus 2. I think that's, it's in numbers is 1 minus 8, 0, plus 8, minus 1, all over 12, all over 12h. 1 over h would, of course, show up here. In this lecture, I may forget various h's, but they're okay. You see the idea. And now here, just to pin this idea down, so this will be example 0. How would I get just a simple forward difference, like uj plus 1 minus uj over h, which is the very, very first approximation you might think of to the derivative. So what would give me that one? Let's do one way down at the simplest level where we can really think it through. What a line, exactly. I would just be using these 2 points. Well, maybe I should improve the figure here. So let me squeeze, knowing I'll need the space, let me squeeze this figure in here. So if I have uj and uj plus 1, and I'm given values there, if that height is uj and this height is uj plus 1, I fit it. I've only got 2 points. Fit them by a straight line. Take the derivative of this straight line at j, and well, it's the slope of the line, and of course that's what it is. So this is degree 1, this is degree 2, this is degree 4, and so on. All right. Now comes the spectral idea. What, instead of just staying with finite, up to 6 or 8 or so on, what if I'm working on the whole line? So in my outline for the talk, we've now sort of covered polynomial accuracy. That's old-fashioned as of today. We're moving to spectral accuracy. And I'm interested in 3 situations. One where I'm on the whole line, which is where I've been here. I haven't worried about any boundaries. Then, secondly, will come a periodic case where the boundary condition, there is a finite interval, but periodicity makes life easy. And then finally, when there's a boundary condition other than periodic, like u of 0 equals 0, the boundary conditions that we've seen, what happens there? Okay. All right, so we're on the whole line. So this is part 1, whole line. Okay. So now I've got the whole line with equally spaced mesh H. I've got values of u at all points here. And I'm looking for an interpolation function, p of x. Let's pin down j equals 0 here as a typical one. I'm looking for an interpolation, sort of the nicest function I can think of, which will interpolate those values, and I'll take its derivative, and that will give me a formula that involves all the u's now. So this first step isn't completely practical because it's going to be an infinitely long differentiation formula, but also infinitely accurate. And what do you propose that I fit with? I can't very well take a polynomial of infinite degree, I don't think. It doesn't sound like the right thing to do. Yeah, that sinc function is going to come in. That sinc function is going to come in. So I'm going to use, and what are some of the other words? You guys maybe know them. So whose formula am I going to use here for producing out of these samples a function? And what's the word that's associated with that type of a function? Band limited is the word I'm going to look at. Right. So these are exactly the right words. The sinc function, band limited. So a combination of sinc functions centered at different points. They're band limited. And who's the recently deceased superstar of this world of Shannon? Shannon. Yeah. So that and earlier, he wasn't, of course, the first. I should mention Whittaker as a predecessor of Shannon, and Whittaker may have given the name, the notation to sinc functions. I'm not sure. Okay, so what is this interpolate? Because we have to know this interpolating function, because we have to know that, and then we take its derivative, and we get all these wonderful numbers. Okay, so since we've circled sinc, let's figure out the interpolate for, suppose j at 0, this is always 0. Suppose it was 1 there and 0 at all the other points. Then I'm looking for an interpolation function that'll fit those values, and we hope it rather decays pretty quickly, but we can't control that, and it doesn't actually decay that fast. And what is that function? Then, well, there are many functions, of course, that take these, that are 0 at all these points and 1 there. I could call it the cardinal function. It's sometimes called cardinal interpolation, meaning there's 1 and all the rest zeros, or like Lagrange. Well, it's the sinc function. So this p of x will be the sinc function. Maybe I call it s of x. And what is it? It's the sine of, now we remember, we've got to make the darn thing come to 0 at x equal h. So I guess maybe the sine of pi x over h would do the job, right? At x equal h, I'll have the sine of pi. X equal 2h, I'll still have the sine of 2 pi. But I want to get a 1 at this point, so I have to, remembering that sine a over a approaches 1, I better put pi x over h down there. And that's my sinc function. That's the famous function. Okay. Known to everybody who works with Fourier stuff. And now what's the function that, now interpolate those values? Well, these values I could think, this I could think of as the values uj, well, how should I think of this? As probably a sum of values uj times the delta function. This was the delta. This is, I am interpolating delta. And now my more general case is some combination of deltas. That's always the story, right? That's the beautiful thing about delta functions, is that they're like so basic, 1 and the rest 0. So now if I shift those deltas over, so is that, am I doing this right? Well, I guess it doesn't matter. Yeah, it doesn't matter whether I write m minus j or this. This should agree with what? What will that sum equal? Well, let me change the notation here to n. Suppose I take a sum from n equal minus n. What I want to do? You see what I want to do? I want to write this series of this discrete function as a combination of delta functions. So, and delta functions are so beautiful. Do you see that? What do I get if what does that sum equal? Well, the only term that comes in is when m equal n, right? Because delta is 0 at all the other points. So the only term that comes in is, so I get um. Maybe I should, if the camera doesn't mind, since I've been using j, why don't I, yeah, okay. All right, so I've written the data as a combination of delta functions. So what's my polynomial then? So p is what? What's p of x then? What's my cardinal, what's my band limited Shannon sinc interpolating series that, so for delta itself, delta 0 we could say, this was the guy. But the process is going to be linear. So if I have some combination with weights un, what should the function be? Shift it over, right? It should be sine of pi x minus n over h divided by pi x minus n over h. I guess that's got to be it. I'll put it there even without checking with Nick Trefethen here. So that's my. Do I want something a little different? Sorry? Oh, the steps shouldn't, yeah, that's right. The steps should be, yeah. Thank you. You can see I'm not really a pro at this at all. NH, yeah, NH. Good. Okay. Now that looks better. Right. So does this do what we want? Does it have this value at the point NH? I want, and I hope I have, P at the point NH should be what? Should be that. Should be UN. That was my idea. Here's the point. There's a point NH, and it's got a height UN. So that's what I'm if I'm interpolating, this is the interpolating condition. Hit all the discrete points right. And this is the function that fills in between those points in this band limited. So what does band limited mean? What's the band? What is it that's limited? Just to remember what we're talking about here. What is it? What does it mean to say that I've produced this band limited function? And of course, this sum is going from minus infinity to infinity. And in a minute, I'm supposed to take its derivative, right? And its second derivative. And come up with magic numbers. You see what's happening here. See, the principle is so nice. Choose an intelligent interpolating p of x, and then take its derivative. Now, can I come back to that question? You'll have to give me some feedback on whether, when I ask about band limited, I'm asking about something you like dream about every evening, so it's absurd, or whether it helps to get that word out here. So where is maybe I need help actually. So band limited means that its Fourier transform, which is, that word's getting used here for the first moment, is limited to a finite interval, right? The Fourier transform, p hat of k, is 0 outside some interval of k's. That's what band limited means, that the frequencies are all in this band, and I'm a little nervous about writing down what that band might be. Maybe I should be able to see it from here. Where are the frequencies here? Help me out. Is it perhaps pi over h? No. H over pi? 1 over 2h? All right. Question minus, all I know is it's all right. We'll put that in. Yeah. Yeah. Okay, yeah, it'll be it will have an h in the denominator, and possibly these pi's that we'll get in our hair in all Fourier formulas. Okay. Anyway, what's important is it's a natural choice, and we can take its derivative, and we can replace this formula by an infinitely accurate formula. And what is that formula? Well, let me just say, thanks to Trefethen, or of course he got it from the predecessor, what those numbers actually are. Yeah, here they are. They are, oh, well, so the derivative, du dx, can I just put down the coefficients and not the values? So the coefficient of the center point is going to be 0, as it was in, here we had 0 uj's, here we had 0 uj's. Everything's, you know, we're working anti-symmetrically here, so we'll have 0 in the center. Of course, we'll have a 1 over h multiplying all these numbers. And we have, I think it's a minus 1, 1 on the sides, and then a 1/2 and a minus 1/2 next, and a minus a third and a third next, and so forth. Oh, well, sorry, I've got the signs wrong, because it ought to, so it's plus there and minus here, plus there and minus there. So, is that okay? 1, I'll erase that plus sign now to make it look clean. Yeah. The numbers are 1, minus a half, 1/3, minus a quarter, and so forth. Okay. Slowly decaying, right? Slowly decaying. The kind of decay that we see in the sinc function itself. And I could figure out the second derivative. Why? Or I could, better than that, I could rely on the Trefethen for the second derivative. So, but it's sort of interesting to know. So here I'll have an h squared, of course. And if I do it, he gets a 1 and a 1. Now, this is going to be the center here. And then there's a minus a quarter, a minus, oh, of course, this is symmetric, right? Second derivative, plus a ninth, plus a ninth. And anybody want to tell me what number ought to go at the 0 position? Well, first, tell me some way to, well, two ways to find it. One way would be, and I shouldn't be so cowardly as to flinch from this, would be to take the second derivative. But you have a pretty shrewd idea of another way to determine that number. What do you think? The sum to 0. Yeah, the sum has to be 0. Because if my function u was constant, if all the values of u were the same, then I absolutely expect the derivatives to be 0. Here, of course, they sum to 0 because there's a 1 and a minus 1 and a minus a half and a half, so the first derivative of the constant is 0. Here, they'll sum to 0 if I put the right number in there, and that right number turns out to be minus pi squared over 6. Okay. So, I think that's right. Well, at least I'm believing it's right. Okay, so now we've done it, really, for the whole line. We found an approximation with infinite accuracy, and now I just have to say what does that accuracy mean? How do we see something with infinite accuracy, infinite order of accuracy? Okay, well, certainly numerically you see it. If you took a function, you know, some reasonable function, took its discrete values, used the formulas, you would see that this is second order accurate. That as h went to 0, you would see in a log plot, you'd see it, of course. And this guy you would see as fourth order accurate. Again, take a smooth function, use its mesh values. Then the polynomial, of course, doesn't reconstruct the function exactly, but it's h fourth accurate. And as h decreases on a log plot, you see that slope of 4. Fine. Well, what do you see with one of these guys? Well, of course, now everything depends on the function. So now I have to pause for a minute and talk about smoothness of functions, right? I have to say something about smoothness of the original function that u of x that I'm working. That's sort of behind the scenes that I'm approximating the derivative of. Okay. Suppose that original function, u of x, that I'm trying to take the derivative of, hasn't got that many derivatives. Suppose it's like a hat function or something. Then what can I expect? So if my original function isn't that smooth, then what could I expect from these formulas? This formula, then upgraded to this one, and then hyper upgraded to this one. What would you expect to see if you compared those? If you looked at let h get smaller and smaller, use more and more mesh values of the hat function. I just made up the hat function as a typical function. You know, I'm taking more and more finer and finer values of it. But still, its problem isn't going away, right? So I guess what I want to say is that the order of the decay on my graph, when I do this little numerical test by using Professor Matlab program, this can't really beat this, because the function isn't good enough. If the function isn't good enough to make higher accuracy possible, then, well, that's its problem, right? We can't, our formula cannot achieve the impossible. That is, get terrific accuracy for a function that hasn't got that many derivatives. Okay. If the function were band limited, yes. No, so that's a good point. Suppose, yeah. Now, so let's here's a non-smooth example, right? Now, so let's just take a minute and discuss infinitely smooth functions, infinite smoothness, because those are the ones which this guy is, totally take advantage of. In the graph, you'll see the error just it doesn't go down like some log deal on a log plot. It's just boom. And so where would functions be infinitely smooth? Well, your suggestion of, suppose u of x the original u of x shall I put orig? Just remember then that we're talking about this original function behind the scenes, not talking about our interpolation. But if our original function u of x, say, is, well, so what are some, maybe this is a moment, this actually anticipates a little my next lecture about Fourier series. What I want to connect, I'm going to use the idea of the Fourier transform of the function. So if I have a function u of x, it's got a Fourier transform u hat of k. And so I'm speaking now just informally about this topic of smoothness of a function and how it's reflected in its Fourier transform. And how is it reflected, generally speaking? If I take this function, which isn't very smooth, what's up with its Fourier transform? Sorry? Say again? It's not band limited, and so it's not zero outside some interval. And more than that, what does it do? So outside, as I approach infinity, it doesn't chop off, and it only decays polynomially, right? In fact, do you know what the rate of decay so it's the decay, the smoothness of the function, it connects with the decay rate of the transform. Maybe we've noted this before. But see it again. So what's the decay rate for this, for u hat in that case? U hat of k, let's remember. I have to work from the delta function. So the delta function the transform as a constant, no decay. Step function, one derivative better, and the u hat would decay like first power. Hat function, one derivative better still, so it'll decay like 1 over k squared. Okay. Now, if the function's band limited, well, boy, then the Fourier transform decays as, incredibly. I mean, it's actually 0 outside the interval. So this is the other extreme. This is like great, extreme smoothness. So this is u hat is actually 0 outside a finite interval. Now, what about in between? Well, yeah. So give me a type of function. Yeah, tell me a function. Here, this is a good question. Tell me a function that's not band limited, so it doesn't have this superstar rate of decay in the transform, but it decays faster than any polynomial, so it hasn't got any delta functions. Even after you take its derivatives, you still don't get any. So Gaussian, thanks. If I took the Gaussian, so a Gaussian's a very good example because the function is e to the minus x squared over 2, and we know its transform is e to the minus k squared over 2, modulo constants. So there is an infinitely smooth function. Actually has, yeah, that e to the minus, what kind of a, yeah, what do you, how would I describe a function like e to the minus x squared over 2? I mean, it hasn't got any singularities, right, in the finite plane. It never goes wrong. And in fact, I can extend it into the complex plane. I can extend it into e to the minus z squared over 2. So this is defined on the real axis, and you say that's where we are. But the properties of a function get revealed also by what happens if you push them out to and now still no singularities. And that's what we see here, this terrific rate of decay. Okay. So this would be, I would call this thing an entire function. An entire function. And these band-limited guys will be entire functions too. They're even better than this, right? So an entire function is a function that you can extend out into the complex plane, and it still doesn't have any singularities except at infinity. There are no poles, nothing bad. You see there's some function theory, some discussion of properties of functions hiding here, and it's the properties of the functions that control how terrific this infinite formula actually is. Okay. So these are totally terrific, and the Paley-Wiener theorem enters to describe. It pins down exactly the property, a connection between properties of functions and properties of a transform. Rate of growth. So this grows a bit fast. So this wouldn't be, Paley and Wiener wouldn't be interested in this one. We're naturally interested in it because we know it's transforming exactly, and it's sort of in between the extreme. I mean, the world's most perfect type of function and the world's non-smooth function and the non-smooth function. Right. Okay. Is that little discussion helpful? Okay. So that's really what I wanted to say about the whole line. Yeah. For which functions is it exact? Oh, that's a good question. It must be probably band limited. Yeah. Because if the function was, yeah. So if the underlying function was band limited and to the same band, and as our interpolator, they'd be the one and the same. Right. Yeah. So I guess we get perfect accuracy on the functions where p of x is exactly the original u of x. Then of course when we take the derivative, this becomes an equation when p is exactly u. So the functions which fit perfectly our interpolation function, then those are the ones we're going to get exactly right. That's a very good point. Okay. Now, what remains to do in this discussion? Well, I've got a ways to go here on this outline. Now I'm ready for periodic, and then for non-periodic. Okay. So periodic, what's up? Fourier is still going to operate, but it's maybe more realistic to think I'm going to have finite formulas. My formulas are not going to go infinitely long, and I'm going to deal with Fourier series somewhere instead of Fourier integrals. You know, and I'll list at the beginning of the next lecture the different Fourier setups. So this was the whole line setup, and now I'm going to an interval, periodic on an interval where Fourier series operates. Okay, our principle is going to be the same. That we will now, this interval will go from 0 to, or 1 to n. 0 to n minus 1 would be, Trefethen reveals himself as a mathematician by not choosing this counting rule. So n is going to be pretty large, though. So what's our differentiation formula? Is not going to be infinite. Where are we? It's not going to be these infinite formulas anymore, but it will be quite long formulas. It'll be formulas of length n. And maybe I'll just write down what he discovers, just because it's just like curious to see what happens. So I'll write them in just above the whole line case. Guess I'm erasing this. We never figured out, or I never figured out what that band was, but it's within our powers. Okay, so can I I hadn't learned this subject, and so it was just naturally interesting to discover what these, it's a 1 over 2, there's a 2 that I can take out. And I just want to look, and of course we're going to have still a 0 on that center guy. And it's periodic, so, okay. Well, it turns out to be the h is not here. It comes in this h is 1 over n. And n is affecting everything now. So I can't expect h to just come out that way. And what it turns out to be is a cotangent of h over 2, and of course minus cotangent of h over 2, and minus cotangent of 2h over 2, and a plus that. Of course I won't write it's anti-symmetric. The next one would be plus cotangent of 3h over 2. Isn't that nice? And so on. And while I'm at it, let me do the similar one for the second derivative. That one, well, it'll have some messy expression in here to make the thing add to 0. And it turns out to be, it's symmetric, of course, now, being the second derivative. And it turns out to be cosecant squared of h over 2. And symmetric, and cosecant squared of 2h over 2, and so forth. Symmetric. So you got cosecant squareds and cotangent in the formulas. Yes. Yeah. Then I better number again. Because he says that if there's one formula in this book to remember, let me tell you the one he says. Remember this formula. Yeah. It's quite memorable. Pi over h is n over 2. That's his, he says remember that. So I don't know how that helps, but I'm sure it's relevant. Yeah, so maybe it goes from 0 to n, but maybe un is the same as u0. Do you think? Where they're probably n. Yeah, they're probably n independent guys, and then un is the same as u0. Good. Yeah. You're totally right. So un will be u0 in this periodic case. Okay. And then we have. Do you see what kind of a matrix are we going to? What will be our differentiation matrix? What was our differentiation matrix here? Yeah. And our second differentiation. Oh well, we've seen these matrices, so we certainly. So what's the differentiation matrix that I would apply to all the list of u's? There would be a 1 over 2h, and then there would be somehow a 1, a 0, and a -1, right? We're good at that stuff. And of course, I don't have to say that in this one it would be a 1 minus 2, 1. And now we're in the periodic case. So what would happen in the periodic case here? It would circle around. This -1 would show up there, and the 1 would show up there, right? We'd have a circulant in the periodic case. And we have the same circulant idea. There's a typical row, and the next row is shifted over because it's centered at j plus 1, and the next row is shifted over, but we loop around from periodicity. So we get a matrix with these diagonals, and it's circulant, looping around, so it's n by n. That's the differentiation matrix, you could say. That's the matrix that you would apply to the values to get values of the derivative. That's really what we're doing here. We're constructing the differentiation matrix, the matrix that you multiply by u1, u2, u3, etc., and get our. Here it is, doing the job. Multiplying u1, u2, u3, so on, and giving u1 prime, u2 prime, u3 prime the derivative. Right. So our matrix is full. That's the point. Tridiagonal here, tridiagonal here, pentadiagonal here, and full here. And here, right? It's a full matrix. So that's, I guess, what Orsag, that's the essence of Orsag's proposal. Anybody really could have seen that, hey, we can get infinite accuracy if we use infinitely many values, right? I mean, that's not surprising. But to say that you could actually work with the darn things, that you could deal quite happily with these infinite, very large and totally full matrices is the whole point. That of course it isn't as simple as working with our tridiagonal matrices, but the point is you can do it, and therefore the spectral methods have, for problems that have got enough smoothness, have become a really serious part of computations. Oh. In real life, that's right. That's right. Maybe this guy, I haven't figured it out, but this is probably periodic. So I mean, this formula is suitably, truncates itself, so to speak. It swings around. Probably when I get to cotangent of, when I've upped this thing by pi, I'm back to. Oh, in the infinite line, sure. So when I did number 1, I was talking blue sky problem, right? Now I'm talking cloudy sky, really, but still periodic. So that's still like I'm making life easy by saying, okay, periodic. And of course, the idea would be use the FFT. Yeah. Yes. 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 Good point. Yeah. What if I use an nth order polynomial and compared it with this spectral method? Good question. And I guess I'm going to have to face that kind of question in the third case, in the non-periodic case, because I'm not really going to be entitled to do Fourier stuff. Yeah. So I'm ready. I'm actually that your question is right on target, particularly for this non-periodic case. What if I fit? So your question would be, what if I fit this thing by a polynomial of degree n? Okay, that's just the right question. So that's what we didn't do here, right? We didn't fit by a polynomial of degree n. We fit by a band-limited type guy, periodic, but periodic band-limited, and it gave us these numbers, which are winners in periodic problems. If I use this differentiation formula in periodic problems, one, I can live with it, even though it's a full matrix, because the FFT is just happy to take matrices, happy to work with a matrix like that. Now, I gotta go to the problem of non-periodic, like our problem in lecture 1. So now I'm ready for part 3, non-periodic, not periodic boundary conditions. For example, u of 0 equals 0 and u of 1 equals 0, our old friend. What do we do now? I could take that interval 0, 1, I could chop it up into n equally spaced nodes, I could fit by polynomial, high degree, I could create the difference formula, and it would be a disaster. A total disaster. And the reason is I started wrong. I should never have taken equally spaced points if I'm going to do high degree polynomial fitting. So this is the final message, that if I want to get this really high accuracy, I better not use an equally spaced mesh. If I'm taking our boundary value problem for a rod, simple second order differential equation from 0 to 1. Well, I should maybe turn it upside down and hang the rod, for example, or the elastic bar. Maybe I'll let it hang. I'll have a Dirichlet condition, 0 value up here, 0 slope, free end down here. Not periodic, anyway. And then the question is, what are the right points to choose? And maybe this is like, it's the right ones are sufficiently memorable that this is a good, so the way we can remember the sinc function for equally spaced points, we got to remember what to do, what's a good spacing of points. And here it is. Well, let me draw the points and then we could figure out the formula. Imagine a circle. Take equally spaced points around the circle and project them onto the axis. So they're cosines, right? The radius was 1 for all these points, and we took the x component, the projection on the x-axis, so those values are cosines. Should I cheat and just be sure I'm expressing the cosine correctly? these are the Chebyshev points. So maybe I emphasize who created these points. And they're the good points. And mathematical analysis has to explain why those points are good, but they are. They're way, way better. No comparison with equally spaced points on non-periodic. Let me get to. Yeah. If you plot any graph, I mean, here I don't know if you can see this graph, or if the camera can. Here is you see how the Chebyshev points are. Of course, you see them. They're bunched at the ends of the interval, because it's the ends of the interval where you got discontinuity. The non-periodicity is killing you at that point. But if you put the Chebyshev polynomials through those points, they oscillate quite nicely. They don't get out of hand. If you take equally spaced points and fit with a polynomial, it takes off at the end of the interval wildly. And any graph that you draw is disaster. And any calculation you do is a disaster. So we see what those Chebyshev points are, and now finally let me just write them down. The cosine of j pi over n. These are the xj's that you should use for. So just to conclude this lecture, without doing the analysis that says why those points are great, maybe the graph helps to explain it, that if I put polynomial, if I put my function p of x interpolating at those points, then it stays reasonable. As n gets large, it doesn't blow sky high. And of course, then I take the derivative and the second derivative. So I'm doing the Chebyshev spectral method. And that's the right set of points for interpolation and for calculations on a finite interval without periodicity. So I left here the applications. I mean, the applications are now straightforward. Once we know how to replace a derivative by a discrete one, that gives us the discrete equation that we work with. If it's an eigenvalue problem, well, so what are some examples here? We haven't spoken about an eigenvalue problem before. What would be a typical eigenvalue problem? The eigenvalue problem, u double prime equal lambda u on an interval, 0 to 1. Well, of course, we could find those eigenvalues exactly, and then we could find them by Chebyshev spectral methods, and we could see, are they any good? And the answer would be yes, they are good. At least the eigenvalues are good until you get up to a eigenvalue where the eigenvector oscillates so fast that your mesh can't see it. So the answer is good. And then what are other ones? Let's see. I think a harmonic oscillator, is that maybe satisfy that equation? So that's a less trivial example than this one, but a very famous and important one. Eigenvalues are great, using Chebyshev points and replacing the second derivative by the second difference matrix. Yeah, and these Matlab calculations just bring it all out. And let me close by referring to Orsag's original result, which brought this whole subject alive. This was 1971. Interesting. 1971. he was computing the instability of plane fluid flow. Poisson flow, special simple flow. And the question was, what's the critical Reynolds number? Right? Between laminar, I'm not an expert and you may not be or may not all be, between laminar smooth flow and turbulence. And the question is, when does some operator, of course the equation is nonlinear, so it'll be the linearization, when does an eigenvalue go off into the unstable half plane? And he computed that the critical Reynolds number was R equal 5772.22. Okay, that was the Reynolds number. And such accuracy had never been seen. And brought this whole subject to life. So that's the kind of thing that real science can be done numerically when you have a method as accurate as this. I only have to add one more point before ending this lecture. That the matrices involved in this example are not symmetric. And Trefethen's whole work over the last 10 years or more has been to say, if a matrix isn't symmetric, its eigenvalues are not the whole story. So that, you see that I'm hesitating to end a lecture which I owe to Trefethen's book without commenting that this eigenvalue, critical eigenvalue, the critical value where an eigenvalue becomes unstable, isn't the last word. In a non-symmetric problem, it's not just the eigenvalues that matter. The eigenvectors play a role. The SVD comes in instead of just the eigenvector decomposition. Eigenvectors can run into each other. So the eigenvalues don't tell you everything. You have to know that the conditioning of the eigenvectors becomes all important. Anyway, so Trefethen's developed this theory of pseudo-eigenvalues. To deal with the non-symmetric or non-normal, non-orthogonal when the eigenvectors are not orthogonal, then this different approach for the people that are believers in it, develop the theory, comes into its own. Okay, that's pausing time, certainly. You see that we used some of the ideas associated with Fourier analysis, that we ended up in this discussion of smoothness about Fourier analysis, and now my second lecture this afternoon will really focus on on what I think are the most useful tools that Fourier analysis gives us. So I'll go from differential equations to the connections between u of x and u hat of k, to other connections between u hat of k and u of x in the second lecture this afternoon. So some of that will be familiar. It's Fourier theory, and I'll try to pick out points that are really key for the applications. Okay, so that's end of lecture 21 and 22 at 3:30.